All right, next topic is LaGrange multipliers. This one's a bit longer and more complicated to explain. So it's an optimization technique, kind of like finding the minima, maxima, and saddle points, except you have a constraint. You don't just have the entire surface to work with. Basically, you have some sort of what's called a constraint curve, or like a line that you can imagine being placed on the surface. So you're basically just looking for the highest and lowest points on that line. So the most difficult part of this is just drawing the connection, like visually, between the constraint curve and the level surface using that same function. So what we have is a constraint curve, which may look like your typical equation, say for a circle. So like x squared plus y squared equals 1. So there's 3 different ways, just to clarify, that you can imagine what that equation represents. So the first way is in 2D, which is just your regular equation for a circle on the xy plane. So the next way is a 3-dimensional way. So if you just take that circle and extend it upwards and downwards in the z direction, it becomes a cylinder. And then the next way is as an elliptic paraboloid. So if you replace the 1 with a z, that's what you get. So in other words, the equation is x squared plus y squared equals z. But if we then keep that interpretation and replace the z now back with a 1, it is now what's called a level curve, raised above the xy plane at a height of z equals 1, and also with a radius 1, just like a circle. So that interpretation is the one that we're going to use to derive the intuition for the LaGrange multiplier. The cylinder one is irrelevant. I just mentioned that, to make sure that we're covering our bases mentally here and we don't get confused. But the circle one is kind of useful because it helps you get a mental image of the overlay of the constraint curve onto the function f. If you were to look down on it along the z-axis or whatever axis, of the variable that's missing in the g equation. Granted, you can also do the same thing with the level curve that we're talking about. It just might not be on the xy plane, such as in this case, where the circle of radius 1 is found as a level curve, but only at a height of z equals 1. But you can still project it onto f in your mind. Okay, so now that we've established that the constraint equation can also be treated like a 3D surface equation, we take advantage of the fact that level curves of a 3D equation have a property, which is that their gradient vectors point in a direction that is normal or orthogonal to the curve within the plane of that level curve. Okay, now the other thing that we have to take advantage of is the fact that some places along the constraint curve around f, and we're not talking about g now, we're talking about the complicated surface f, will also have gradient vectors be parallel to, even if not in the exact plane of, the level curve of g in that same xy position. And those spots only exist on the constraint curve of f, where it's a maximum or a minimum. So in other words, here's the whole point how this works. What we can do is we can set an equation saying that the gradient of f is equal to the gradient of g, and then solving it will give those few spots where the constraint curve has a max or min. The only other thing is that even if the gradient vectors are parallel, they could have different lengths. So in other words, we need to add some constant multiplier to the equation to account for this. And you'll typically put it on the side of the equation containing the g. And that constant is what we call lambda, i.e. the LaGrange multiplier. So all of that was just to build up in the intuition to sort of visualize and conceptualize how this technique came to be. So anyways, to actually do a problem with LaGrange multipliers, here's what you do. You just write the equation that I just mentioned. So in this example, that equation can actually be broken into two equations, which is that, the I hat component of f equals the I hat component of g, and the j hat component of f equals the j hat component of g, and you can keep on going if there's even more dimensions. So on top of that, we have a third equation to continue using the same example, and that third equation is the constraint curve equation, which is x squared plus y squared equals 1. Or more generally, so that we can apply it to other examples, think of the equation g equals k. So k in this example is 1. So anyway, we have three equations and three unknowns. So the unknowns are, again, x, y, and lambda. So now we just solve it algebraically, and that's basically it. How you do that is going to differ slightly based on what equations you get. So I'll just leave it, as a general statement. But a general way that you can start solving it is to take the partials with regard to f and g, then set f sub x and g sub x equal, and then set f sub y and g sub y equal, etc. for as many dimensions as you have, and then solve them for x or y. And then this will give equations containing lambda, which we can then sub into that equation g equals k and solve for lambda. Then you can plug lambda back into those previous equations that we just solved to get x and y values. Once you have those x and y values, plug those pairs back into f to see what they give us. And the highest number, of course, is going to be your max value given the constraint, and the lowest number is your minimum value, along the constraint. And you can have more than two extrema if you have additional local maxes or mins. So that's that.